Here we're going to talk about the interference of sound waves. We've talked a little bit about the interference of waves in general. Some of those waves we can see, but some we can't. And we can't see sound waves, but they still interfere the way that all other waves can. So we've talked about the principle of superposition, and the idea that if we have two waves that meet, the displacement of the medium at a particular location is to find that displacement. We just add together the displacements from the individual waves at the same location. So if I have two waves that are out of phase, like so, where the crests meet troughs, those two waves will add to give me zero displacement, and we call that a node. So we get no energy at that point where those waves meet. If I have two waves that are in phase, that's taking a lot longer than I thought it would, then that means that instead of crests lining up with troughs, we would have crests lining up with crests. So I'll draw two waves that are in phase now. There's one, and there's another. And when we add those two waves together, then we get a greater amplitude. So we'll get a really big amplitude wave that looks something like that, because we get what we call super crests, where those two crests add to give us a bigger displacement. Here we can see it's really big, and we get a super trough too, when that displacement increases like that. So if we have the two waves that are in phase, we call that constructive interference, because the displacement increases. And so we would get the super crest. And if we have two troughs interfering, then we get the super trough, as I mentioned previously, like so. And the first example I looked at, we have waves that are out of phase, which means that we'll get a crest adding to a trough, and we get a displacement of zero. As long as those are the same size, we get no energy at all. If they're different sizes, then we get a little bit of energy, but it will be reduced compared to the energy of the original pulses or waves. So if the amplitude increases, what does that do for the wave? What does that mean? Well, that would give an increase in energy. If you think about a water wave, the greater the amplitude of the water wave, the more energy it carries. So a tsunami, for example, or a tidal wave, has a huge amplitude, and that's why they can be so destructive, because they carry so much energy. So if there's more energy, there's more intensity. It's a higher intensity with a greater amplitude. Sometimes we call that the volume of sound, but that doesn't really make sense. That's kind of a common slang term in a way. If you turn up the volume of the stereo, what you're really doing is you're increasing the sound intensity in the room. Volume, of course, is a measure of how much space there is, so that's a bit deceiving using that term. I try not to use it. Although it would be fun to have a stereo that could change the volume of the room. Turn up the stereo and the room gets bigger. They haven't invented that yet, I don't think. Here we can see a drawing of what a sound wave would look like if it were a high-pitched sound. Like a ee sound would be high pitch. Lower pitch, or lower frequency, would look something like this if we could see it, or low frequency, low pitch sound. Of course, we're drawing these as transverse waves. Remember, a transverse wave looks like this. A sound wave is actually a longitudinal wave, which means you have areas of rarefaction and areas where the particles are closer together, areas of compression we call those, and then rarefaction, and these alternate. But it's really hard to draw longitudinal waves, so we will often draw sound waves as transverse waves. even though they're not transverse waves. Transverse. Here's one of those technologies you've probably run across with regard to sound. Noise reduction headphones. Sometimes these are called noise canceling headphones. I believe these were first used with aircraft pilots who needed to reduce the sound that they heard from outside the aircraft, so that they could hear their communications from radio towers or control towers easily for safety reasons. So with noise reduction headphones or noise canceling headphones, they can reduce the sound that they hear from outside the headphones, so they can hear the sound they want to hear more clearly. So the sound coming from outside is half a wavelength out of phase with a sound that is produced by a speaker inside the headphones after the microphone inside listens to the sound coming from the outside. So this little microphone here records the sound from outside and then changes its phase by half a wavelength. So we have the crests become troughs and the troughs become crests, so that when the sound gets to the ear, the sound from outside the headphones is combining with the sound created by the speaker inside the headphones, which is half a wavelength out of phase. So those crests meet the troughs and they get to your ear and they give you zero energy. And then there's sound that you want to hear, your music or your radio transmissions, whatever the case may be. Those sounds are separate, and those are the only sounds that you hear, because now the sound from the outside has been canceled or reduced to zero energy with the sound wave interference. If two frequencies are significantly different, then we get an interference pattern that's repeating, and they sound musical. So it's pleasant to hear. I think most people would agree. And that happens if the ratio between the frequencies is a small whole number ratio. So we say that that's consonance, or it's a consonant sound. If the ratio is exactly 2 to 1 for those frequencies, then we say that those sounds are 1 octave apart. So this is what that would look like if we combine those two sound waves. And that's a sound that you'll hear in music, and it's quite pleasant. If the resulting interference pattern is a ratio that's not a small whole number ratio, then that's called a dissonant sound, and we get an unusual pattern there that's generally not pleasant to hear. So here's an example that's 37 to 20. That would probably not be heard in music very often, because most people wouldn't like hearing that sound. Now what happens if we have frequencies that are nearly equal and they're only slightly different? Sometimes the interference is constructive and sometimes it's destructive, which means the intensity increases then decreases, and that will happen repeatedly if the sounds are continuous. So you get loud, quiet, loud, quiet, loud, quiet. And that's called beats. So if you hear the sound increasing in intensity, as we see here, and then decreasing in intensity, as we see here, over and over again, then you're hearing beats. So it's kind of a wow, wow, wow sound. If you're a guitarist and you've ever used a tuning fork to tune your guitar strings, then you probably know what beats sound like, because you'll pluck the guitar string and then strike the tuning fork, and if you can hear that sound, then you know that those two frequencies are close to being equal, but they're not they're not the same. So you need to adjust the tension in your guitar string until those beats go away, and then you know that the frequencies are the same and you've tuned your guitar string. There are newer devices that you can use to do that. There are electronic means of tuning guitar strings now, but I'm sure a lot of people still use tuning forks. Keith Richards probably does. So, if tuning forks of 255 Hz and 257 Hz are struck simultaneously, then beats will be heard at a frequency of 2 Hz, or in other words, 2 beats per second. The closer the frequencies are, the lower the beat frequency will be. So if you're tuning your guitar string, you want to hear those beats less frequently. So if you strike the tuning fork and pluck your guitar string and you hear the beats going wah 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 wah, then you want to hear those reduce in frequency to wah wah wah. Then you know you're getting close. And then when they reduce so much that you can't hear any beats, now you know that you've tuned your guitar string properly because the two frequencies are equal. So if you wanted to calculate the beat frequency, then you can do so with a pretty simple formula. Beat frequency is equal to the absolute value of F1 minus F2. I should have made that a lowercase f. Lowercase f for frequency. There we go. So beat frequency equals the absolute value of F1 minus F2. So we subtract the two values in this case. So we get 255. So in this case, absolute value of 255 Hertz minus 257 Hertz. Oops, that's an absolute value. And we get 2 Hertz. The absolute value just means that if we get a negative, we ignore it. Your math teacher will give you a better definition, but when we're using this formula, if we just want the beat frequency, we just want to know what's the frequency of those sounds we hear. We're not interested in which frequency is higher or lower, so the negative there doesn't really matter to us. Let's try an example with beats and the Doppler effect that we've looked at before. So a car with a siren of 550 Hertz is driving toward an observer at a speed of 5 meters per second. Another car with a siren of 550 Hertz is parked beside the observer. What is the beat frequency heard by the observer? Let's assume that the speed of sound in the air is 344 meters per second. So, for the moving source, here's our Doppler effect formula that you might recall from earlier on. So we'll put the speed of sound in there and we'll substitute the frequency of the source as well. So we get the observed frequency of 558 Hertz. And this is when the source is approaching the observer. That's why we use the negative there. You'll remember that the observed frequency depends on whether the object is moving towards the observer or if the source is moving away. And so we've got the beat frequency is the difference between those frequencies, and we can take the absolute value again just in case we'll get a negative, although in this case we wouldn't. So we get 558 Hertz minus 550 Hertz, or 8 Hertz. Of course, what is heard by the listener will depend on the location of the listener. So in other words, if the source were moving away, then that would change the frequency, the observed frequency, due to the Doppler effect. You can work that out on your own if you want, see what that comes out to. Now if we have two sources of sound, for example, here we've got a couple of speakers, then those two sources will produce an interference pattern as well. Here we see that that's a two-dimensional version of what we've seen in one dimension before. So when we used our springs to create interference patterns on the floor, that was in we could describe that as one-dimensional wave interference, because those waves were either moving back or forward, and they would interfere when they came into contact with each other. Here the waves are moving out in all directions, and so we have two-dimensional wave interference here. on the screen, but if we were to listen to these sounds, really it would be three-dimensional wave interference, because we could hear those sounds anywhere in the room in 3 dimensions. So we'll get areas of constructive interference, which would give us an increase in sound intensity. We might call it volume, but I think it would be better to call it increase in intensity. And those would be the areas that we would call antinodal lines on the screen, or antinodal spaces if it's in 3 dimensions. So here's an antinode right there. There's another antinode, antinode, antinode. So if you were to walk around through the room, which we could do in the lab with a couple of speakers, then walking around through the room, we should be able to walk through those areas of high intensity. So you'd walk along and you'd hear loud then quiet, loud then quiet, loud then quiet as you move around the room, as long as these two speakers are emitting a constant sound with the same frequency. And we can try that in the lab. So in between those loud areas, we would get the quiet areas, and those are the nodal spaces. Or on the screen, they look like nodal lines. So the blue ones there, that's where you get the low intensity sound, so there's less energy there. So those are the nodal lines, or in 3 dimensions, nodal spaces. Or if you want to call them nodal volumes, and that's why volume is kind of confusing. Nodal volumes means a 3-dimensional nodal space. So again, I'm going to call that intensity, not volume. So those are those nodal areas, nodal spaces where the sound is quiet. Now, you may have places where you want to deliberately trap sound or prevent sound from moving around and reflecting, because it could be that there are loud sounds produced and you don't want people to have to hear loud, distracting sounds. And so we can use special structures on ceilings, and we can use sound baffles, that's what these are called, which will help to prevent the reflection of sound waves from the surfaces, so that we don't get sound transmitted into other rooms, and we also don't get sound waves reflecting around the room that we're in. Public pools can tend to get pretty loud with all the sound reflecting, and so if you have sound baffles on the ceiling, they can help to absorb some of that energy or prevent it from reflecting in a regular way, so it won't be quite so loud in the room. Our science labs are right above a gym, and so I think we have sound baffles attached to the gym ceiling in order to try to prevent the sound from traveling up into our science labs that comes from the gym. An inexpensive way to do this is to use egg cartons. If you have a room where you're producing a lot of sound, say you've got some machinery and you're doing a lot of work and you don't want your neighbors to hear the sound, you can get some egg cartons and tape them to the walls, and that's a very inexpensive way to make some sound absorption structure, so that the sound won't transmit through the wall as well, and it can be quieter for your neighbors. And it would probably be quieter for you too. So that's sound wave interference.